Hi, I am Joe from Learn at Home. In this video, we are going to learn about complement representations. This topic comes as part of many different subjects like computer architecture, digital system design, and even in microprocessors. And this is also a very important topic as far as competitive exams are concerned. So let's get started. Complement representations are generally used in digital computers, and they are generally used to represent negative numbers in a digital computer. The advantage is that once you are able to represent a negative number, arithmetic operations can be drastically simplified. It means that uh, the way in which a digital computer performs arithmetic operations can be simplified, especially the subtraction operation. As you may be aware, there are two types of arithmetics defined. One is the signed arithmetic, and the other one is the unsigned arithmetic. In unsigned arithmetic, we are not bothered about the sign of the numbers. That means if I can say that a plus b, I am not bothered about the signs of the numbers. They are assumed to be positive, and I just mean the magnitude of a plus magnitude of b. But in signed arithmetic, we are also bothered about the signs of numbers. We That means we are bothered about negative numbers as well. So it means that I can write plus a plus minus b. So this means that I am representing the signs as well with this. So this is actually nothing but a minus b. So the idea here is that once we are able to represent a negative number, so if you are given with a number b and you need to find its negative counterpart, that is minus b. So once we are able to represent minus b in a proper format in binary, then you can do this. You can perform this a minus b. So what you just want to do is that you need not do a direct subtraction. What you can do is that a plus minus b. This is the operation which is done in digital computers. So again, this minus b, the calculation of minus b is based on a particular complement representation, which we are going to study now. Let us now learn about the types of complement forms. It is defined like this. For a number system with base r, the following complements are defined, that is r minus 1's complement and r's complement. So for example, for a binary number, as you may be aware, for a binary number r is equal to 2. That means the base is 2. So we can have r minus 1, that is 1's complement, and r's complement, that is 2's complement. And the complement forms are not only limited to the binary system, it can also be applicable, it can also become applicable to the other number systems as well. But in fact, they are commonly used with binary number system. We are bothered about only 1's complement and 2's complement because they are used along with digital. The purpose is to represent negative numbers in digital systems, and we are only bothered about a binary number system there. But it is very much possible that we can also have complement forms with respect to other number systems. For example, a decimal number system can have complement forms. As you may be aware, for a decimal number system, r is equal to 10. The value of r is going to be 10, and the possible complement representations are 9's complement and 10's complement. 9's complement and 10's complement. Now let us look at the definition of complement forms. For a given number n, there are two definitions, that is the r minus 1's complement and the r's complement. The r minus 1's complement is defined like this. It is given by r raised to small n minus 1 minus n. Here, small n represents the number of digits in the number of digits the number of digits in n. And let us look at the binary numbers. Let us consider the binary number system where r is equal to 2. We know that r is equal to 2. And let us find out the value of this r raised to n minus 1 for different cases. Like if you consider a 3-digit binary number where n is equal to 3, let us find out the value of r raised to n minus 1. Now that becomes 2 raised to 3 minus 1. And 2 raised to 3 minus 1 is equivalent to 7. And the equivalent binary representation of 7 is 1, 1, and 1. And now let us look at another case where the value of n, the number of digits, is 4. Then what we need to find is 2 raised to 4 minus 1, and that is 2 raised to 4 minus 1 becomes 15, and the equivalent binary is 1, 1, 1, and 1. So we can generalize that the value of r raised to n, the value of r raised to n minus 1 is a series of ones, and it is equal to the series of ones with n number of ones in that, where n is the number of digits in n. So with this idea, we can try to find out the r minus 1's complement of a binary number. Let us take an example. So let me erase this. So consider a number. Let us consider a number 1010, and let us find the r minus 1's complement of 1010. So the number that we have is 10. That means the capital N is given as 1010, and small n here is the number of digits. In this case it is going to be 4. And now when we find r raised to n, that is 2 raised to 4 minus 1, we know that this is 15, and the equivalent binary is 1, 1, 1, and 1. And as per the definition of r minus 1's complement that we have seen, r minus 1's complement is defined as r raised to n minus 1 minus n. That means I have to subtract n from this. That means my n here is 1010, so I have to subtract 1010. So when I do that, I will get here 1, 0, 1, and 0. So if you compare these two things, that is 1010 and 0101, you can find that this is the exact complement of the original number. So we can say that this ones complement of a binary number. To find the ones complement of a binary number, what you need to do is only to invert the bits. So whenever you see a 0, just change it to 1. Whenever you see a 1, just change it to 0. So that will give you the ones complement. Now let us try to understand what is 2's complement for a binary representation. So for a binary representation, we'll have 2's complement. And don't forget that the general representation of 1's complement is r raised to n minus n. Now let us look at the general representation of r's complement. The r's complement is defined like this. It is equal to 0. If n is equal to 0, and it is equal to r raised to n minus n, for all n not equal to 0. n. For n not equal to 0, it is given by r raised to n minus n. So when you compare the 1's complement or the r minus 1's complement with r's complement, this is the formula for, this is the representation of r's complement, that is r raised to n minus n. And the previous one, that is r minus 1's complement, is represented as r raised to n minus 1 minus n. So from these two boxes, you can identify that the r minus 1's complement plus 1 will give you the r's complement. So this is an important result. R minus 1's complement plus 1 will give you the r's complement. And in our case, we considered the number n. So in our case, if you want to find the 2's complement of 1 0 1 0, what we need to do is to find the 1's complement first, that we have already done, and just add 1 with that. And we have already found the 1's complement, that is 0 1 0 1. And to find the 2's complement, what I need to do is just add 1 with this number. So I just want to add 1 with this number, then I will get 0 here, and then there's a carry of 1, then there's no other carries. So this is the 2's complement representation of 1 0 1 0. So this is the 2's complement, and this number out here is the 1's complement. This is the 1's complement, and this is the 2's complement. Now there are two important things to be remembered. One is that the 2's complement of a 0 is 0, and the 2's complement of n is used to represent minus n. This is what we were talking about it in the first slide. So the 2's complement of n is used to represent minus n. So if we are able to find the 2's complement of n, then that becomes the representation of minus n. In the earlier slide, we have seen an example of this. We have taken n is equal to 1 0 1 0, and we have found the 2's complement of n. The 2's complement is found like this. You have to just invert what is given, that is 0 1 0 1, and that becomes the 1's complement, and then add 1 to that. Then you will get 0 1 1 and 0. So you can understand that this is the 2's complement representation. So this actually represents negative of n. So always remember that the 2's complement of n is used to represent negative of n. So here any given number, you can find the 2's complement, and it actually represents its negative form. Now there are some tricks in finding 2's complement of n given the number n, and also the reverse, that is n from its 2's complement. Let us look at the easier way of finding the 2's complement from a number, and the number from its 2's complement. Now let us take an example. Let us take n is equal to 1 1 0 1 1 0 0. Now the easy way to find 2's complement of n is to scan the number in this direction until you see a 1. So you can see that this is 0, and here you see a 1. So stop there, and just copy that down, 1 0 0, and now invert the bits that is after that. That is here, this one is inverted as 0 1 0 and 0. This becomes the 2's complement of the number. This is the 2's complement of the number. And And so finding the reverse case, that is finding n from its 2's complement, can also follow the same procedure. For example, you need to, for finding n from 2's complement, what you need to do is the same procedure. That is, you need to scan from this scan in this direction until you are finding a 1. So in this case, this is 0, this is 0, and this is 1. Stop there, copy those 1 0 0, and then reverse or invert the bits after that. Then that means it is 1 0 1 1. You can verify that this was our original number. So if you are given with a 2's complement, you can easily find the original number n. So these tricks can be applied when, in competitive exams, so that you don't waste much of the time. So the normal way that how we calculate is, it takes time because you need to invert this and then add 1 to that. But this can be done in a lesser time, so it will help you in competitive exams. Hope you had a happy learning. We at Learn at Home are always committed to produce quality educational resources free of cost. And if you have any suggestions or would like to support us, please contact us in the mail ID shown. Thanks for watching. This is Joe from Learn at Home signing off.